Hey everybody, welcome to the first of our demo videos. So over the next few weeks I'm going to continue to pump out from time to time some Jupyter notebooks that are going to help you come to grips with how to actually implement all the things we're talking about theoretically during the lecture. Okay? As I mentioned in the lecture this last time in Wednesday, I'm just not going fast enough during lecture, right? So in previous times I've taught this course, I've integrated these notebooks into the lecture. We just can't do that. So I'm going to be recording these as separate lectures. Each one will be relatively short. And the notebooks themselves are available to you. So let's take a look at where you can grab a hold of them. So here in my GitHub, Jason G. Fleischer, UCSD _COGS 118A, you can have access to all these notebooks. Feel free to clone them out and bring them down. Not all of them are up because I'm revising them as I would go. So each week there'll be a new batch of them, 1 or 2 each week. Okay, and they're going to drop into this notebooks directory right here. Right. Important to note that if you may also want to look at some of the other things, right now I've got local copies of the textbooks that we use, Bishop and the Hasty book and the Mackay book are all in here. I will probably put other stuff in here from week to week. Okay? Great. So if you want to use these notebooks, like I said, you can clone it down to your local, or you can just go ahead and click on one of the notebooks, and after it loads, they have this little Open in Google Colab button. So you can immediately, hopefully, click on this. Now, in my world, my computer, it's set up to block pop-ups, so I've got to actually purposefully open it, and you will get in Google Colab a live version of this notebook that you can play along with. So feel free to go ahead and do that. All right, well, let's start with this first notebook. It is feature representation. So back in, as we were talking about the math lecture number 2, we talked a little bit about how we can do things like one-hot encoding. Okay, but it's not just categorical data that we need to be careful with. In fact, any data, we may do a variety of manipulations to. So generally in machine learning, many things, and especially things that are not deep learning, many things you're going to take the data and you're going to engineer it. You'll have some raw data. You'll do stuff to the raw data to try to make it more amenable to the learning process. Now, it's not that all this idea of engineering features goes away with deep learning. I shouldn't give you that impression. But some deep learning setups are all about trying to create the features themselves. Okay? That's just an FYI, because this is not a deep learning class. All right, but for almost every other kind of machine learning, we're going to try to take the raw data, and we're probably going to not feed the raw data into the algorithm, but we're going to massage it in some way to make it something that is easier for learning algorithms to deal with. So we're going to talk first about some of the things you're going to use here. Okay? So you're going to see this throughout all the notebooks. I'm going to be using some very standard toolkits that are in Python. Okay? So we're going to use NumPy, like you know. We're going to use scikit-learn, and I'm going to use a lot of pandas for data manipulation. Hopefully you've seen some of these in COGS 108 or a similar sort of class. Okay? But just as you know, NumPy is for doing matrix algebra. Pandas is for dealing with data. All kinds of ways you can take data, and pandas can make it easy for you to manipulate data and process it. Okay, scikit-learn is our standard machine learning toolkit that we're going to employ, and some other things will be specialty, but one that I like a lot, Seaborn, is actually like matplotlib. It is a graphing and figure making toolkit. It extends matplotlib, it makes matplotlib better, and essentially it enables you to deal with matplotlib style graphics at a higher level, something that's a little bit more akin to some sort of I want to get task X accomplished, so I'm going to have an interface that's specific to task X. Okay. Seaborn conveniently, and actually scikit-learn as well, by the way, packages several nice data sets for us to use. So the first things that I'm going to do is I'm going to import these libraries. Yes, I know, I'm not Google, sorry. Okay, so we're going to import these libraries and we're going to load up the penguins data from Seaborn. Okay, what does this data look like? It has some categorical elements to it. There's the species, which is, there's 3 different penguin species here, the Adelie and the Gentoo, and I forget the other species right now. And they happen on 3 different islands, so where they're found. And we have measurements of the birds, their bill length, their bill depth, their flipper length, their body mass in grams, and their sex. Okay, so we end up with 333 penguins in this data. Now, important to note that this setup here, this data, is set up like our design matrix. Okay, samples are going down in rows, and features, variables are going across in columns. Okay? Well, so let's take a look at things like bill length and body mass. All right, so if we're going to do machine learning stuff, it can be the case that high value numbers can start to dominate some kinds of machine learning algorithms. Okay? If one of the variables is orders of magnitude larger than the other in terms of the raw number being put in, some machine learning algorithms will come to pay attention to that very large number and ignore the very small number. So something that is usually one of the first things you're going to do for most machine learning algorithms, essentially whenever you don't know for sure that your algorithm is immune to this problem, then you should probably take a whack at taking all those reals and turning them into some sort of standardized format. Okay? Now, normalizing it or standardizing it or whatever you want to do is probably going to be a process that's dependent on the data. There's no one right answer. It depends on the data and the algorithm, what the right approach to take is. So you can do things like taking all the training data and call the biggest thing in it 1 and the smallest thing in it 0. Okay? And rescale everything linearly. It's called a min-max scale. Okay? You can do things like you can take and turn it into quantiles, right? So this in the training data, this is the 0th percentile, this is the 10th percentile, this is the 50th percentile, that is the median value, right? And so on and so forth. Okay, and then you can rescale everything on percentiles. Well, I'm going to show you, all of those exist, by the way, in scikit-learn. They're easy drop-in functions. Okay, but I'm just going to show you right now the standard scalar. The standard scalar is the Z transform for those of you that remember your statistics. So what is that? Well, what we do is we find the mean of the data. So if I'm going to standard scale bill length, I'm going to calculate the mean bill length. And then I'm going to take every bill length in this data and I'm going to turn it into how many standard deviations away from the mean am I. So a very, very small bill might be -2 standard deviations from the mean, and a very, very long bill might be +2 standard deviations from the mean. So we're going to turn it into standard deviations, and that's what the standard scaler does. So let's take a look at doing this piece by piece. First, what we're going to do is we're only going to standardize the real valued columns. So we need to get rid of those columns which have categorical information. Okay? So that's what I just did here. I dropped out species, island, and sex. Okay? Let's take a look at what we've got left. Okay? So pandas data frames like this, you can just call histogram, and they'll generate a histogram for every column separately, every variable in the data. All right? So here we can see the distribution of bill length, bill depth, flipper length, and body mass. So none of these look very, very normal, right? So flipper length looks distinctly bimodal. Body mass is very skewed, right? So we know that some kinds of statistics certainly are going to have problems with this if we took a very statistical approach. If we were trying to do linear regression, it might not work so well. Okay? I'm going to break normality assumptions. So let's see what happens when we do a z-transform, when we use the standard scaler. Right? What are we going to do? How do we use the standard scaler? Well, so we've already imported standard scaler from scikit-learn, so now it's just a function in this notebook. Okay? So all elements of scikit-learn have very similar interfaces. So each thing is a class, and the class has methods we can call. Okay? So we can, once we have an estimator, is the base class of all of scikit-learn. Once we have any estimator, then what we can do is we can fit it to data. So we can take that estimator class, like standard scaler here, and we can call fit, and call fit with some data x. All right, and we're going to fit the estimator. Once the estimator is fit, we can transform new data. Okay, so you can think of that like we have a machine learning algorithm, we fit it to the training data. And then after we have it, we can predict new data, what the output should be. Okay, so you're going to have that same format. So once the standard scaler is fit, we can transform it. Or in this case, we can use the fit transform method to do it all at once. Okay, so we can fit the standard scaler, and then we can get the output of the standard scaler on the x. Okay, so that's, this whole thing generates the data. We create a new instance of the standard scaler class, and then we simultaneously fit to the data, and then get the outputs, get the standard deviations that are going to replace the raw data values. Okay? So that's generating the data. The rest of this is just turning the output of standard scaler into a new data frame. Okay? So we're creating a new pandas data frame here. If you're not familiar with that process, I suggest you go check out COGS 108 tutorials. Okay? So here we go. What we've done is each one of these columns is separately being turned into a z-score. So the first few bill lengths that were 39 millimeters-ish are apparently about -0.9 standard deviations, almost one standard deviation lower than the mean. Okay, so there we go. We've got standardized scaled data. Let's take a look at the standardized data. Okay, does it look more normal? No, it does not. Because what we did is we just z-transformed the data. We didn't do anything to make it more normal. We took the mean of the data. It's just that the mean of a bimodal distribution is just a regular mean, and turning that into standard deviations just maintains the bimodal distribution of flipper length. Okay? Well, what are some things, some tricks that we might do to turn data more normal if that's what we need? A very standard thing to do is to log transform it. Log transformation, or turning something into the square of itself, or something like that, are tricks that will start to make a little bit non-normal data look more normal. It doesn't solve everything, right? It's not going to solve everything and make stuff look normal, but it will make things generally look more normal. All right, let's take a look at it. So after log transformation, which by the way, we just use pandas apply method here. Okay, so we just ask the pandas data frame, we already have X, we apply to each and every column in X the logarithm of that column. Okay, so we just turn that into, literally we log each column separately, and we get a result out that I'm calling X of L, and we get a histogram. Okay, what happens? So the bimodal stuff doesn't go away, but it's starting to squish together, right? And the body mass has a lot less skew in it. It's still not perfect, but it is definitely less skew. Okay? So we see what I said. We don't solve issues, but we make them less awful. And we can even do both at once. Okay? So we can take the output of logarithm and we can run it through a standard scalar. Okay? So it's important to note here, right, what happened as we went down, right? Look at body mass back when we started. Body mass was, heading for 6,000 grams. And, over here we had build depth, which was 20 millimeters. Okay? After a scalar transformation, build depth and body mass both top out at 2. We get that situation where algorithms won't start to prefer to react to body mass instead of to build depth. Now they have equal magnitudes. Okay? A log transformation by itself didn't really solve that issue. I mean, it made it significantly better, right? But there's still some scale issues of a factor of 2, right? No longer a factor of 100. So when we do both at once, we get both benefits, right? We have less non-normality, and we have pretty much the same scale. Okay? So there we go. We have transformed all of this data, all of this real valued data, into potentially more useful formats that will enable us to do machine learning algorithms with more good feelings about our outcomes than if we didn't do these transformations. Okay? All right. Well, there were 3 categorical variables in the data. Let's take a look at them. So there are 3 unique species. Chinstrap was the species I couldn't remember. Okay, nice little pandas thing here. If you take a column and call unique on it, you'll get all the unique values in it. Okay, so the islands are here, Torgeson, Bisco, and Dream. And of course, the sexes are male and female for these penguins. So, what do we see? Well, we know that if we turn these 3 species or 3 islands into the numbers 1, 2, or 3, we are inducing some kind of ordering, right? So encoding them like literally 1, 2, and 3 as a ordinal variable is one thing that people might do, but it can get you into trouble. Okay? It can get you into trouble because when you induce ordering, you can fool some algorithms into thinking that, chin straps should be more similar to Adelies than Gentus. Or sorry, I should say that chin straps are closer to Adelies than Gentus are, right? There's not necessarily true in the data, but if we ordered Adelie, chin strap, Gentoo, then 1, 2, we would assume in our algorithm that 2 is more closely related to 1 than 3 is to 1. Okay? That's not necessarily the case. That's not necessarily the relationships we want our machine learning algorithm to discover, and we're going to bias it to discover them by the nature of that encoding. So, to fix all this, we go to the one-hot categorical system, right? The one-hot categorical system is going to put in, for every category, we're going to have a brand new column, right? So the category Adelie will get a new column, and every penguin sample that we have will have either a 0 for Adelie or a 1. If it's a 0, this penguin is not an Adelie. If it's a 1, this penguin is an Adelie. And likewise, we're going to get chin strap column and gen 2 column. And everything in that columns, we're going to be 0 and 1. And as you look across the 3 columns, only one of those binary digits is going to be hot. Only one hot. The other values are going to be 0, and just whichever penguin it is going to be 1. So penguin species are mutually exclusive. You can only be one of the species, and so we're going to have a one hot encoding where only one of these binary digits can be turned to 1, and the rest of them have to be at 0. All right. So once again, scikit-learn has provided us with a one-hot encoder. It's a class that we imported at the top of this notebook. And as I said before, every single estimator in scikit-learn has this interface, okay, the same interface, where we can fit it. Way, good job, Jason. All right, so where we can fit the data, right? So we instantiate a new one-hot encoder by calling it with empty braces. We're going to get the default parameters of a one-hot encoder. And now we're going to cause that encoder to be fit on the 3 categorical variables. Let's take a look and see what comes out. Okay. So our encoder has built into it now, it knows the categories in the data. It knows these 3 categories in species, and it knows the 3 islands, and it knows the 2 sexes. All right, but we have not yet turned our data into a one-hot. We just trained the one-hot, which means that we figured out what categories are going where. Okay, so now we take our trained encoder, right? Take our trained encoder down to this one, and we're going to transform that same data. Okay, now I need this data not as a data frame, but I need it as an array, as a numpy array. Okay, and I'm going to do that next. Okay, so I'm going to take the data, and in the end, I'm going to turn it into a numpy array. Sorry, it doesn't come out as a data frame. My bad. It comes out as a numpy sparse matrix. That's the issue. So a numpy sparse matrix is not printable. Okay, it's just a memory saving kind of thing. So we need to turn it into a dense matrix in a numpy array. So that's what the toArray command does. All right, let's do the transformation. So what comes out? Just what I said would, right? We're going to have the first 3 columns are going to be, this is the Adelie column, this is the chin strap column, and this is the gen 2 column. All right, and these last 2 columns are male or female. Sorry, female is first, then male. Okay, and the middle columns, including the ones that the printing elided, are, those middle 3 are those islands. All right, let's replace the data in the data frame. Okay, we made this guy here way up above, right? That is the standard scalar version of the real data. So x of s, right here, here is x of s, right? It's z transformed real data. There's no categorical data attached to this data frame right now. All right, so we're going to add on new columns for each category. We're going to put the transformed 1s or 0s in for the appropriate one. All right, let's do that. And now we have just what I promised. Adelie is a column which is either 1 or 0. Likewise, chin strap or gen 2. Okay? And they are all mutually exclusive, these three. Bisco, Dream, and Torgeson, the islands, are mutually exclusive, and so is female or male, these two columns. So we have now turned all of our penguins into, all of their penguin data into data which has all got the same magnitude, right? So it's all roughly on the order of 1. So the binary digits are 1 or 0. The reals can go up to like kind of -2, 2, but that's a minor difference. It's not really going to bias it too much to prefer that. If it was an order 10 difference, we might be more worried. Okay, so we can put all this training data in, and we can assume that our machine learning algorithm is going to react just as strongly to changes in bill length as it will to changes in species. And it's not going to confuse species that, you know, that one species is more similar than another. Okay. All right, so let's take a look at the data that comes out now. So we're going to histogram it again, so we can see the same sorts of distribution of the real values that we had earlier, and we can see that all of the categorical variables are 0s or 1s. All right. Lastly, I'm not going to belabor this because we're not really going to do this much in class, but one last way in which we might have a lot of encoding issues is if we have things that are not naturally in one-dimensional vectors, right? So we don't naturally have the ability to break out into this variable, then this variable, and this variable, right? One of those things is an image. In an image, you have a two-dimensional arrangement of data. And you could imagine that you might like to preserve some information about the natural arrangement, that these pixels are more close to each other than this pixel and this pixel way up here. Okay? But we can't really do that in principle with a vectorized input. All right? So there's no one way to solve this, and the default way in which you will often see images done is to ignore it. Okay, let's just pretend the problem doesn't exist, and we're just going to turn the two-dimensional array of data, or potentially three-dimensional array of data, into 1D vectors. All right? So as I said, I'm not going to belabor this. I will let you explore this a lot more yourself. Okay? But in the meantime, feel free to play with this and see how it works. But, you know, here is the first easiest example where all the data is merely in grayscale. So it's either, you know, black or white or shades of gray in between. There's no color space. And so you literally just turn that two-dimensional array into a one-dimensional array by rowing it. Okay? So here is a bunch of data which has on the left zeros and on the right's 200s. So most image data is going to be between 0 and 255. It's going to be an 8-bit description of intensity, right? So what do you think this array turned into an image is going to look like? Bueller? Anybody? For some reason, you're not answering me. I can't imagine why. All right, so it's going to be on the left, it's going to be a black square. And on the right, it's going to be a medium gray square, because it's not quite 255. So let's go ahead and show you what that looks like. Right? This turned that array into an image, and it's what I just described. Okay? Now, realistically, you're usually going to be operating with color images. Color images, each pixel has red, green, and blue. Okay, so each pixel is now a 3-long vector. And to turn it into vector, we're going to just unroll it on the 3, and then on the rows, and then on a row, and then across rows. Okay. So let's take a look at this black and yellow image that we just created, where black is 0, 0, 0, right? And yellow is all the red, all the green. So there is your image of black and yellow, right? So as I mentioned, we're going to take this RGB data, which is in a 3-dimensional format, and we're just going to squash it down to 1 dimension by unraveling it as described here. Okay. So that's going to look like this. All right. So, and then we can do a bunch of other operations. We can get more. Oh, good. All right. I guess I'm going to have to double check that that got stuck into the GitHub. Good job, Jason. So you can get more data, and you can stack it up and make a data frame is what's supposed to come out of this. And that data frame would contain these 2 images in separate rows, just like we had rows of penguins earlier. All right. Well, that's an excellent way to end our first demo. I hope you all enjoyed it. As I said, most of these are going to be on the 15-minute mark. This one got extra long because I had to introduce a lot of stuff. All right. But good luck. Talk to y'all later.